Hi, my name is Jason Lobdell, and I'm going to be discussing exam question 36, going over supervised learning and reinforcement learning, as well as their implications within AlphaGo, and some of the significance behind these AlphaGo systems. So supervised learning. Supervised learning has three key characteristics, that being passive observation, the use of a teacher, and function approximation. So passive observation is interesting because the system itself operates within an environment and it doesn't really alter the input space that it's responding to. So these inputs are all going to be independent from one another. Now these inputs are going to be a part of a labeled data set given to the model by a teacher or supervisor. So this supervised learning operates with an input-output pairing system. Given an input, being able to predict the output of it. Now, the teacher aspect comes into play because the teacher not only provides the training data set, but it also uses feedback and error backpropagation to evaluate the accuracy of these input-output pairings. So from there, you take an output and you try and use some kind of measure of accuracy and compare it to the input and make sure that that's all kind of aligning with one another. So that kind of leads us to function approximation, selecting a function that closely matches the target function in a task-specific way. So for example, keeping in mind that the goal of supervised learning is to predict an output using a labeled input data set. An example of this would be a labeled data set of animal images and telling that model whether an image is a dog or a cat, and then using that model, providing it with a new image and trying to make it compare that new image with the provided labeled data set and then trying to predict the correct label. So this is useful for things like object recognition and classification problems, being able to predict a discrete value and identify an input as a member of a particular class. For reinforcement learning, this is a little bit different. Now, this involves active observation. So this is going to be interacting with the environment and changing the environment it observes. If you notice in the bottom right, you'll see a kind of cyclical dynamic interaction between agent, environments, and rewards. So the agent's actions are going to influence the environment, and the environment observations of the environment are going to influence that agent and its actions. Also, you have the rewards that come from the environment. So how does the utility of their actions affect their future actions and so forth? So that's one thing to focus on with reinforcement learning is expected utility. So in this case, you're trying to reinforce with either positive or negative utility. So either reward and punishment respectively. Now this kind of comes into play with the methods of exploitation or exploration. So using reinforcement learning, you can try to seek out the most reward from the observed past. So this would be exploiting. Or you could explore and try to seek out novel information in an attempt to evaluate different reward options and kind of figure out which one's better. An example of this would be a chess game. So here you can either exploit and do the same openings that you might see from chess masters, or you might try and go the exploration route and do things a little bit differently and evaluate the utility of different movements, whether you're going to lose a pawn or a different piece, a rook, etc., or maybe you'll take one instead. And so those are some things to think about when we talk about reinforcement learning. So how were these used within AlphaGo? So AlphaGo used supervised learning through labeled data sets of human expert moves. So they've already provided this data. Reinforcement learning came from self-play. So this kind of learned what kind of moves were good and bad based on the outcomes of the game. Did it win or did it lose? Some other key components of these systems were convolutional neural networks and as well as a Monte Carlo tree search. So AlphaGo, as we know, was very monumental in the fact that it defeated one of the highest ranked players in Go. And this was monumental for AI because this really showed us that these systems have a much higher power, both physically in their computational skills, but also in their ability to play these games. So when we compare AlphaGo to some of its descendants, like AlphaGo Zero, we kind of notice a little bit of a difference. AlphaGo Zero relied on reinforcement learning only. It was taught exclusively by itself. It wasn't provided any of these labeled data sets. So it didn't play human-like Go. It strictly learned from itself. It became its own teacher and was designed to predict its own moves, selections, as well as the outcomes of such. So what are some of the significances of these two things? Well, they showed us that AI has far and beyond surpassed the human ability in these games. It also taught us that the capability of these systems is completely different, whether it's taught by itself or it's taught from humans. When it's taught from itself, it has a superhuman playing ability. Pattern recognition in this case outperforms that of what humans are capable of. This also showed us that new concepts to creativity and novel experiences are also much more possible than what a human could imagine. It also, AlphaGo Zero, more specifically, showed us that we can save a lot of time and resources in machine learning. We don't need to go out and provide data label sets. If we can teach the algorithm to learn from itself, play against itself, and learn from scratch, it's going to even outperform the systems that we provide with labeled data sets. So this is going to be really interesting to kind of see in the future of how we can formulate ways to predict environments and as well as the outcomes using these methods of machine learning. Thank you so much for your time, and I hope you were able to take something away from this. Thank you.